Hey, and welcome to this video on time series forecasting. My name is Mike Mastanduno. I'm a senior data scientist with Health Catalyst, and today we'll be talking about how to get more out of your data. So without further ado, I will share my screen and let's get going. So we're talking about time series forecasting, and this is forecasting like the weather, as in you get to know the future. But unlike the weather, we're using your data, which could be any kind of time-oriented data. Where does this fit into the data science overall offerings? It actually fits into level 1, the guided analytics, which is how you got here. We're talking about just this little piece here, the forecasting component. So the first question is, what is time series forecasting? And so if we had some data, in this case, it's inpatient census versus date, and so a daily grain, we can see like over about a year and a half, we have some busy periods, some quiet periods, it slowly increases. And then, as we get towards the end of the series and zoom in a little bit, the obvious question is, where is this data headed? Where is our inpatient census going? And that's kind of exactly the intuitive response to what time series forecast tries to do in a mathematical way. So to put a little more specificity on the why, time series forecasts orients us towards the future, which is the only thing we can actually change. Computers are very good at separating signal from noise. So our goal here is to say, if a pattern or a trend exists in data, we can find it and use it as much as we can. We're not going to latch on to trends or seasons that don't actually exist in the data. And so what that'll do is give the most accurate context to decision makers. We're not trying to replace the boardroom. We're just trying to put the right information in front of leadership who's making decisions around, say, inpatient census, for instance. There are 3 types of forecasting that are worth mentioning. The first is the automated projection, which is just applying computer algorithms to time series data to project future performance. Or there's the accepted forecast, which is to say that accountable people have looked at that automated projection and agreed that if history is a guide, that projection is accurate. And then finally, there's the evented forecast, which is where people can say, well, if we make this change to our workflow, here's what we can expect for the expected forecast to become. And those could be things like organizational investment in a new policy or things like that. So far, we're really only going to be touching on number 1 and a little bit on number 2, but that's where we all start, so that's fine. So time series forecasting, how does it work? That's the first question. Like, it's not a black box, or we don't want it to be that way. So time series forecasting is going to use only the time series data and no additional information. So this is not a predictive machine learning model where you're going to feed in lots and lots of information about age and gender. Time series data is only concerned about what, in the example of inpatient census, what the inpatient census was in the past. It doesn't care about the weather or the phase of the moon or anything like that, the number of car accidents or whatever. It only cares about inpatient census. And then the forecasting algorithms they're gonna pick apart that time series and decompose it into, into seasonality, for instance. So if we have our data here, we can see it has this cyclical seasonality. Maybe that varies with day of the week or year, or season of the year. And so the algorithms will figure that out. They'll see that it has an increasing trend. And then these algorithms will also get information out of lags. So if today is a Monday, what did last Monday look like? What did the Monday before that look like? If it's a Wednesday, how does the beginning of the week affect today? And then recent history. So in a way, we are building features and more information, but again, it's all coming from the time series. And so because of that, missing dates and missing data, which are different, are really problematic. We can't feed a forecasting algorithm that's missing like October, for instance. It's going to be looking for that pattern and needing that repeated October. We can't just leave that out. And then data, so if we don't have information for October, we can't use it, and therefore we need to fix it. And replacing with 0 is a bad idea because the algorithm is actually going to say like, oh, there's a 0 in this October, and that could destroy any patterns that would have been there. So fixing the underlying issues is really important, or just truncating the data if the missing value is far enough in the past. And when I say far enough in the past, I mean 2 years for yearly data, or a couple of months for daily data. So really, we want to see that period. If it's years or quarters, we want to see a full period repeated at least twice before we can do useful things with it. Which gets us to, how do we interpret a forecast? So if we have a forecast, we're going to see our historical data for most of time, and then we see what we call a point forecast, which is the forecasted data into the future. And that's based on the algorithms, picking apart that time series and learning the patterns in the data and saying, this is the most likely thing in the future that I can discern from the data. There's going to be a 95% confidence interval. In some cases, it might be 80%, but that's kind of the window of 95% of the time the data would have fallen into this window. And so you'll notice that it gets bigger as it goes out into the future. And that's because, just like the weather, our forecasts are more accurate for shorter amounts of time into the future. The other thing you might see occasionally is what's called a model fit. And so that's, here I've overlaid the blue line onto the data, and that's like what the model actually fit to the data. But you have to remember that the model fit is not the same as predictive performance. It's merely, this is what I understood about the data, and then the point forecast is the resulting, and here's where I think it'll go. That doesn't mean that this model fit is what you would expect to see in the future. For that, we actually need a different tool called holdout forecasts, which are geared to measuring predictive performance. And that's what we're interested in. We want to know, if I sit down and look at this forecast on a Monday morning, will I be able to tell what my inpatient census is 2 Mondays from now, 14 days later? And so holdout forecasts are the way we do that and assess how accurate these forecasts actually are in a predictive sense. And so if we look at a zoom in of that data set and cut it off right here, for instance, on November 1st, we can make a point forecast. And now, because that's in the past, we actually have historical data to compare it against and say, here's what we predicted on November 1st, and then what did it actually do in the subsequent 14 days? And we can do that again on January 1st, and then we can do that again on February 1st. And so we see that, as we build these up, we get more and more forecasts to compare against the real data. And if you did it every day for, say, 120, 4 months worth of data of holdout forecasts, you can start to get a pretty good idea of what your performance looks like 14 days into the future. So here's what that looks like for this data set. We have the black line being the actual data and the blue line being what we predicted 14 days earlier. And you can see that, a lot of times we do match up pretty well. So like this week right here, we nailed it. 14 days ahead of time, we knew exactly what was going to happen. But then the very next week, we were off by quite a bit. So this also helps us address the question of how many days in advance can we trust this forecast? And so looking at, like, this is the 14 days in advance graph. If we were to look at 7 days in advance, we still see some misses. We still see some hits, like here's a big miss. Here's a series where it hits pretty well. And then we can look at 4 days, and we can actually quantify that and say, so again, here's 14, 7, and 4, so you can compare. And we're trying to ask the question, what would history have looked like if we were using this forecast for decision making? And so we can quantify that with a what we call mean absolute percentage error, meaning how many percent wrong were we on a, you know, overall. And so for this data set, it was 6.3% for the 14 days, and then down to like 4.6, 4.7 for the 4 to 7 day range. And so if you were actually to then put this in front of accountable people, you'd be able to say, yeah, we're within 5% when we look a week out. And, you know, that's often going to be good enough for your application, but it depends on what your application is. So that's kind of, and that's how you would assess predictive performance. So then the next question is like, how should you trust the method? Should you trust the forecast? You know, we're doing all we can mathematically, but what does that mean? And so, you know, and a good example is like, we can draw a perfect fit through the number of husbands a newly married woman had, but that doesn't mean that tomorrow she's going to have 2 and the next day she'll have 3. It just means that that we need to think as well. So that's the part where the humans come back in and are actually, you know, still quite important. We don't predict the future. We just look at it and use it as a tool for decision making. The good side of that is that forecasting methods and algorithms have been studied for decades, and 4 rigorous competitions have shown that automated software can do as well or better than professional forecasters who have access to subject matter knowledge. That was done in 1993 on hundreds of data sets. And then in 2000, it was repeated on thousands of data sets to say that simple forecasting algorithms do just as well or better than the complicated ones that we've invented since then. And these competitions are ongoing, and they give us a lot of confidence in our choice of methods. So the method that Health Catalyst has implemented in the guided analytics solution was the second most accurate solution out of all of the different algorithms that were tested in these competitions. So, you know, we're doing about as well as the math will allow. And that's really cool because it means, one, that if a signal doesn't exist, you'll get a flat line as your forecast. And 2, if a signal does exist, this is your best chance at finding it. We don't have to make up whether or not that data means something anymore. And so how do you get started with this? Well, we have access to the Guided Analytics API using ClickView and ClickSense for all of your dashboarding needs. We have Leading Wisely integration for forecasting. And then we have the API itself, which you can call from R, Python, C#, whatever language you might want, with documentation at the HC Data Sciences Services address. And then we're currently in limited analytic accelerators, such as the COVID-19 elective surgery recovery accelerator. And we'll be coming soon to care management, Power BI, Tableau, and more widespread analytic accelerators. So thank you, and it's been very nice.